Welcome to the Math Record. This video will cover part 1 of chapter 1 in our calculus class. In this video, I'll introduce the concept of calculus. Okay, let's begin. The idea of a calculus might seem daunting, but it's actually pretty simple. Calculus is basically a collection of ideas explaining the concept of change. You might heard of this term before, which is really basic, which is used for like slope and like anything that's like transitioning from one state to another. So calculus is the idea if we combine a bunch of these changes together, like at really small amounts, we could get something that is a larger idea, which is usually done with slopes or with area. So this might seem vague, but the idea of calculus is basically made out of derivatives, integrals, and sequences in series. There are also other elements like parametrics, polars, and vectors, but those concepts we'll be covering at the very end of class, which we won't be going more in depth of. The fundamental ideas that we'll be covering on would be the derivatives, integrals, and sequences in series. Those are the main three concepts that we'll be tackling, which are the general foundation for calculus. So, the idea of derivatives okay, is to basically find velocity and acceleration. You might have heard this in physics or like elementary math or in like from like algebra to pre-calculus. The idea is that derivatives is if you get something from like if you have a graph, you have something from position versus time, or time versus position. It's the same idea, just have position in the x-axis. Time in the x-axis and position in the y-axis, which you just graph from one motion for like a graph. So usually you have like a polynomial, right? Sorry about that. We have something like this, right? So we could have like time here and position. So let's say you have right here, and this is time, let's say 5, and this is position at y is equal to 7, right? So basically at like 5 seconds, it's at 7 away from its original position. So that's the basic idea for like position versus time or time versus position. So for this concept, we'll use those graphs to find the derivatives, which is usually to work with slope. So as from that same graph, right? Usually for slope, you choose 2 points and then you make a line through it, right? So for the idea of calculus, we want these points to be as close as possible such that these points will merge into one small point and then we could find that slope through one point. It might seem strange that you could find a slope between for just one point rather than basically two, but that's the idea of calculus, where you have really, really small changes that you can actually find an actual numerical answer. So, which usually sometimes happens. Sometimes it doesn't, but for graphs, for simplicity, we'll say it works. So for these graphs, if you have the slope, right? Well, let's say the slope is between these 2 points, but we want to find the slope here, right? Usually this line would be called the average slope, right? Or average rate of change, basically. But so when you have two slope, but you really, really want to find the slope like in that portion of the graph, like precisely at one point. So when you have a slope at that one point, it's called the instantaneous. Sorry, EOUS. I'm running out of space. Sorry about that. But basically, that portion is called the instantaneous slope. INST, like instant, and then ANEOUS slope. So that's instantaneous point. Instantaneous slope is at one point, while a average slope would be from 2 points. So as those 2 points gets closer and closer to each other, so let's say this point goes down this line while this point goes up this line, as they go closer and closer to each other, the let's say we have a position 1 right here and position 2, so you have time 1 here and time 2 here. As the distance between those times get closer and closer to each other, let's say this is the distance, as it gets smaller and smaller to each other, it finally gets into one point, and that one point will give us that slope. And that's the idea of derivatives, which we could use this to find, for those position times, we use these to find velocity. And then for those velocities, we could graph those points to help find the acceleration, which is basically a slope of the change in slope. And then you could also use those, um, the slope of the slope to find like more of slopes. This is usually the concept of like higher order derivatives, which might seem really like really hard, but it really isn't. Okay, now for integrals, that's basically the reverse process. So instead of using position and time graphs to find a velocity, we use velocity to find a position. So this is generally done using an area under a curve. So we have this curve, right? And then we could use like really small changes in calculus to find an area under this curve. So usually this is done by sorry about that. We could have really small rectangles as we put those under the curve, which they have equal difference in base. So let's say all these are length 1 for the base, right? And then you have to find the area sum all the areas under these rectangles to find the area of this curve. And then to get more precise answers, basically you get even smaller and smaller areas. I mean rectangles. So you get more smaller and smaller rectangles. Like instead of saying it's 1, let's say each of them is 0.5 now. So now you have more rectangles, and you could get more areas that are under the graph, and it gives you more precise rectangles under the graphs, and you get more precise areas. This will be the concept of integrals, which uses the idea of changes in small changes in area, which you could combine together to get a really close approximation of an area, and which you could combine together to finally find the exact area of the area under a curve. You could also use this idea to also find the concept of areas for actual shapes. So let's say you have a straight line and you put that line down, and that makes like a right angle. So basically, you can find the area of a triangle, which uses those ideas to actually prove these methods and why an area of a triangle is 1/2 times base times height, which you could also prove using a rectangle. But in calculus, those proofs also work in the same way. And then we have sequences in series, which basically uses sequences and series to find approximations for graphs and actual numerical answers. So this is usually done by, let's say we have a trigonometric graph. So we have sine of x, right? Usually the graph looks like this. Sorry, my picture is bad. But basically, for sequences and series, we could use those ideas to find one point on this graph and find the numerical answer. This is usually a decimal answer, but we could get really close approximations using sequences and series. Another way, a concept that they could also tackle, relating back with the sine of x, would be instead of writing the equation of a sine of x, we could use this as we could change these graphs into polynomials. So let's say we have a polynomial that has goes through this. It doesn't look like it, but let's say we have that polynomial. Now we have that linear to make a quadratic, right? So let's say we have something like this. So we kind of have that first curve, right? And then we can have a cubic, and then we could have a quartic, and then we can have a fifth root, a sixth root, a seventh root, a eighth root, right? And you see how that becomes sort of like a sine graph. So if we have really small increments in change of the polynomials and how they work, we can actually somehow formulate an idea to have how to substitute these trig functions with actual polynomial functions. And that's the idea for sequences in series. All these concepts deal with the idea of change, and we use them to determine a variety of concepts and approximations, which is the general gist of how calculus works. In the next video, we will tackle the concept of limits in case you aren't familiar with it as an introduction to derivatives. Thanks for watching, and I'll see you at the next math record.